With this next example, we're looking at how to calculate entropy change for a phase change substance such as water or one of the refrigerants. I'll start off by reading the problem statement. A rigid tank contains 5 kilograms of refrigerant 134A, initially at 20 degrees Celsius and 140 kilopascal. It is now cooled while being stirred until its pressure drops to 100 kilopascal. We want to know what is the resulting change in entropy. So all we're looking at right now is what is the change in entropy of the substance. So here our system, we have our 134A in a tank. So our 134A is a phase change substance, and a tank is a closed system. There's no mass transfer in a tank. Next thing is we will talk about the conditions. We'll do the sketch last on this one since this is a closed system. We can actually draw the properties sketch. So for the conditions here, we have a closed system. That means constant mass. We have a rigid tank. That means constant volume. And we also have closed and rigid, which remember from chapter 3 is constant specific volume or isochoric process. For the properties, we're given the mass is 5 kilograms. We have the initial temperature is 20 degrees Celsius. Initial pressure 140 kilopascal. And final pressure is 100 kilopascal. Now one thing we notice here is that it tells us that the refrigerant is being cooled and it's also being stirred. So really that is saying that there is heat transfer and there also is some sort of work transfer during this process. We're ready to go ahead and start solving now. So the question is asking what is the change in entropy of the refrigerant during the process. So for delta S, we have delta S of a phase change substance. We find that in the notes. We basically calculate mass times the change in specific entropy. So in order to calculate the change in entropy, we need the mass, which we were given, and the specific entropy at state 1 and state 2. So let's look at our states. First of all, state 1. At state 1, we know the temperature and pressure. So what we need to do for the phase change substance is to determine the phase, first of all. So we compare our temperature, T1, to the saturation temperature at pressure P1. Now this is for a refrigerant 134A. So I'm going to turn on the lights here and grab the book for the properties table. So I'm going to the properties tables for our 134A. That's going to be table A. For 134A, it starts in table A10. So I'm looking for the saturation temperature. That's going to be from table A11. So from table A11, at a pressure of 140 kilopascal, that's going to be 1.4 bar. Our saturation temperature here, I'm going to bring it up. We see at 1.4 bar the saturation temperature is negative 18.8. So our temperature 20 degrees Celsius is greater than the saturation temperature, which was negative 18.8. So at state 1 we have a superheated vapor. So that's state 1. Phase. Now we can get the property value that we're interested in. Here we're interested in specific entropy, S1. So S1, we're just going to look up the value of specific entropy at P1 and T1. So for the superheated phase, we need to go over to the superheated refrigerant tables. R134A, that's going to be table A12. And then we're going to get into the pressure is equal to 1.4 bar subtable. And we're looking at a temperature of 20 degrees Celsius. We're reading off the value of S. Here it looks like 1.0532. And the units that we see there for specific entropy, kilojoule per kilogram times Kelvin. Alright, so that's state 1. At state 2, we know the pressure. So we were given the pressure at state 2, but we don't have any other properties given in the problem statement for state 2. So where can we get the other property? Any ideas? So usually what we do if we don't know a property value at the final state, remember we have to think back to our closed system analysis from chapter 3. If we don't know a property value, then we typically would go to the conditions. And we would look at the conditions and see if there's anything in the conditions that could help us. So in this case we have a closed and rigid process, or in other words an isochoric constant specific volume process. So that's what we're going to need to use also at state 2, is that the specific volume at the final state is equal to the specific volume at the initial state. So for our second property value at state 2, we're actually going to need to look up V1. So we look up V1 the same way that we did S1. We have specific volume at the given pressure and temperature. My dyno is frozen, so just wait a second. I'll go ahead and pull it up in the book. From the book we are in the pressure is equal to 1.4 bar subtable. And at 20 degrees Celsius we read the specific volume 0.16520. My dyno is still, it just paused, it says not responding. Just be patient 1 second please. Still waiting just for dyno to respond. Alright, maybe here it comes. Alright, well maybe while dyno is coming up I can, here it is. Alright, so we have V at the given pressure and temperature was equal to 0.16520. That's kilojoule per kilogram Kelvin. So now we have two properties at state 2. We have specific volume and pressure. So what we need to do to determine the phase here is check our specific volume against the V sub g value and V sub f. So V sub f at our P2 and V sub g at P2. We're going to go into table A11 at 1.4 bar. We read off the V sub g value. Sorry, not 1.4 bar anymore. P2 is 100 kilopascal. So at 1 bar, we read that V sub g is 0.1917, and V sub f looks like 0.007258. So our value 0.16 is in between those two numbers. Alright, V sub f we read as 0.007258. And V sub g, we got 0.1917. These are in meters cubed per kilogram. And actually I should erase this unit was actually specific volume, so it's in meters cubed per kilogram as well. Alright, so last thing to do is calculate the quality, since we are in between V sub f and V sub g. We have a saturated mixture, so in order to get property like entropy, we need to calculate the quality. So the quality here, we can solve x2 is equal to the actual value minus V sub f and again my dyno's frozen for a second, I apologize. Divided by V sub g minus V sub f. So that's what we're going to use to calculate quality. So let's start bringing some of this into our calculator. First thing we want to make a note of is S1. So here S1 was equal to 1.0532. Next, we had V2 and V1. V2 is equal to 0.16520. Then V sub F2 was 0.007258. V sub G2 was 0.1917. MATLAB is taking its time as well, I apologize. So now we can calculate our quality as V2 minus VF2 divided by VG2 minus VF2. So our quality here is 0.8563. So now we can look up S sub F at P2, S sub G at P2. So reading off S sub F and S sub G, we're in table A11. We're in the column that corresponds to a pressure of 1 bar. Here's S sub G, 0.9395. Here's S sub F, 0.0678. So F sub F, 0.0678. S sub G, 0.9395. Units on both of these are going to be kilojoule per kilogram times Kelvin. I'll just write it once. Then we can find S2 finally as SF plus X times SG minus SF. So that's just using the quality equation that we know very well by now. So calculating S2, we end up with S sub F, 0.0678, plus that quality we just found, times S sub G, 0.9395, minus S sub F, 0.0678. That gives us S2 of 0.8143. Now everything is known and we can plug back into our original equation to get delta S. Delta S was mass times S2 minus S1. So if we use our calculator and wrap it up, ds is equal to the mass, that was 5 kilograms, times S2 minus S1, and we end up with negative 1.19. And I'm still frozen, I apologize again. Our change in entropy is negative 1.19. Units here, we're multiplying mass times specific entropy. So mass is in kilograms. That'll cancel off the kilogram and the bottom of specific entropy. And we are left with units of total entropy, kilojoule per kilogram. So we ended up with negative 1.19 kilojoule per kilogram. The last thing we're going to do here second once we get unfrozen is to plot this process on a TS diagram. So you may be wondering how the change in entropy of a system can be negative. Alright, remember we have to distinguish between entropy change and entropy generation and entropy transfer. So entropy generation is the only one that must be positive for the process to be possible. Entropy change and entropy transfer can either be positive or negative. So entropy transfer and entropy change can either be positive or negative. So it's not concerning to us that the entropy change is negative. And actually that should be expected because the entropy transfer was negative because the heat transfer was negative. Alright, let's finish this off by sketching on the TS diagram. So here we have a phase changer. Going to sketch our saturation dome. And we'll go ahead and sketch a process line. We have our initial pressure, 140. and our final pressure was 100. For our initial state, we had a superheated vapor. In our final state, we had a saturated mixture. And we know that the change in entropy was negative. That merely means that S2 is smaller than S1. So whenever we sketch here S1 in the superheated region at P1, I want to make sure and sketch S2 at a point left of S1. That means that S2 is less than S1, or delta S is negative. And then we don't really know the direction of the process here. Since it was isochoric, constant specific volume, it's not constant pressure along this line, it's not constant pressure along this line, it's not constant entropy, so it's not vertical, it's not constant temperature, so it's not horizontal. So we can just leave it as a horizontal dotted line. Alright, main things we were talking about in this problem was calculating delta S of a phase change substance. Remember, delta S, the entropy change, can be positive, negative, or zero.